This talk includes several slides which were provided by Antonio Crisantemou from the SKA Observatory. So here's the outline of my talk. I will introduce the SKA. Then I will talk a bit about SKA Regional Centers because these are relevant to delivery of data to the users, and a little bit about timelines and milestones in the construction of the SKA. In the second part of my talk, I will talk about Indian participation in this project. I'll briefly describe the work that has been done so far and the work that we are currently doing and our future plans during SKA construction. The SKA Observatory is an intergovernmental organization. It's governed by a treaty which has been signed by the various countries. It was officially born on the 4th of February 2021 when several countries came together and signed the treaty. So far, 8 countries which are listed here are full members. 3 other countries are very close to obtaining full membership. They're awaiting final ratification from their governments. There are 3 countries which include India, which are currently part of the project through some kind of interim agreement. And there are 2 countries, Japan and South Korea, which are in the early stages of joining. The SKA is going to be one observatory. There's going to be a global headquarters in the UK. And there are going to be 2 telescope sites, which we'll look at in a minute. There's going to be the SKA mid site, which is in South Africa. And then there is the SKA low site, which is in Western Australia. So on the picture on the left shows you the headquarters of the SKA, that sort of odd-shaped building that you see in the foreground with the Jodrell Bank telescope in the background. Is where this building is where the headquarters of the observatory is located. It's also the mid telescope is going to be located in South Africa, and it contains dishes. That's the technology being used. And in Western Australia, we have the SKA low telescope, which is composed entirely of stations made up of dipole arrays. Both the sites in South Africa and Australia have been selected for their extreme radio quietness. They are extremely remote places, places where density is measured not in terms of people per square kilometer, but in terms of square kilometers per person. It's an extremely expensive project. The total project cost is expected to be about 2.1 billion euros. And it will be operational towards the end of this decade. Here are some numbers about the SKA project. The construction cost alone is about 1.3 billion euros. Operations will also cost significant amounts of money. It's going to take about 8 years to construct. There are going to be more than 100,000 antennas, dipole antennas in Western Australia. There are 197 dishes. 16 countries are participating already, and more may join in the future. What's most interesting is that this telescope will produce 700 petabytes of science data, which has to be delivered to the science users. Remember, this is science data. It's not the raw data. The raw data is much larger. So this, of course, requires a global network of data centers to deliver this science-ready data products to the users. And it's expected to be operational for more than 50 years. And therefore, one has to do some real long-term planning. So the observatory will be run from the global headquarters, but there will be engineering operation centers and science operation centers and science data processing centers in the telescope host countries. So this is just an outline of how the model for the data flow is. What I'd like to draw your attention to, that what is present in the box on top is what constitutes the SKA Observatory. But outside of the SKA Observatory, what you see below are the SKA Regional Centers. These are not officially part of the observatory. They're not even funded by the observatory. But as we shall see in a minute, they are critical to delivering the science from the observatory. So here's a summary of SKA Low, 512 stations, 256 antennas. There's going to be a dense core of about 1 kilometer in diameter. And then there are going to be 3 log spiral arms, 74 kilometer baselines, up to 74 kilometers. And it's going to operate at the low frequency end of observations, go from 50 to 350 megahertz. It'll give you the full bandwidth instantaneously. SK Low in Australia has, the SK Mid in South Africa has 133 dishes. This is a combo of dishes of 2 different types. There are going to be new SK1 dishes of 15-meter diameter, which are going to be constructed, but they are going to be combined with the existing 64 Meerkat dishes. Even here, there's going to be a densely populated core that will give good sensitivity to low surface brightness features. And there are going to be 3 log spiral arms with 150 kilometers baselines. And this will operate from all the way from 350 megahertz to 15 gigahertz. The highest frequency receivers are not going to be constructed immediately, but they will arrive a few years into the future. Here's a sort of layout of the 3 log spiral arms and the dense central core. The telescope operations, the entire control and monitoring of these telescopes will happen at these SOCs, or Science Operations Centers. These are co-located with the Science Data Processing Centers, but note that these locations are far away from the telescopes in both these countries. And therefore, this places extreme constraints on the kind of reliability and availability that is possible with these telescopes. They will have a number of conventional features, which we already have in existing radio telescope facilities, periodic observing proposals. There's going to be service observing, so nobody needs to visit the telescope. There's going to be flexible and dynamic scheduling and 24/7 operations. The complex, challenging features in the case of the SKA is this one, which I already mentioned, operations from a distance. And one needs high operational availability in order to make full efficient use of the telescope. It needs to respond rapidly to transients and target of opportunity observations, and it needs to support subarrays and commensality. Observing modes are all the standard observing modes: imaging mode, the beamforming mode, and the transient search mode. Proposal types will include standard PI-driven proposals, but there will also be large proposals, which are called key science projects. Long-term proposals will also be supported. And there could be coordinated proposals between the 2 SKA telescopes themselves and between the SKA and other telescopes across the world. Commensality should be possible, which will allow, subarrays will allow execution of more than 1 observation project at the same time. And different kinds of subarray configurations will be possible. There could be a core subarray, there could be core plus spiral arms subarray, or the whole array could be partitioned in interesting ways. Commensality will be driven by 3 types of commensalities: data-driven commensality, where different projects use the same data products for different science goals. There will be observing commensality, where different projects use the same signal data for constructing different data products. So they'll have different workflows in the science data processor. And then, of course, there will be multiplexing. You simply configure the telescope into subarrays and then do simultaneous observations. Central to the operations of the SKA Observatory is going to be the monitoring and control system. And it's labeled as telescope management, which you see in this green box towards the center of the image. And that, you can see, is going to be responsible for environmental operating. It's also going to interact with the observatory data archive. It's also going to receive instructions from the SKA telescope operator. It is going to interact with the local monitoring system of the dish or the station. It's going to interact with the science data processor or SDP. It's also going to interact with the engineering management system so that maintenance schedules, etc., are taken into account while scheduling. This central nervous system of the SKA is something that India is heavily involved in building. We'll come to that in a moment. The most challenging part of the SKA is the gigantic data flows through the telescope. The SKA low telescope will produce about 9 terabits per second going into the correlator, and what will come out of the correlator is about 8 terabits per second. And then you need a 130 petaflop supercomputer. This one will be located in Australia, which will spit out data at the rate of 100 petabytes per year, which will be transported over 100 gigabit per second connections to SKA regional centers located across the world. The numbers for SKA mid, as you can see, are similar. That will also produce about 300 petabytes per year. Managing the data flow is one of the biggest challenges for the SKA. The scale and versatility is very important. Large data rate, which requires very robust signal transport as well as compute power. So here's a zoom of the same thing. So the data as it flows out is going to, the final data that you need to store or process is about 45 to 85 petabytes of raw data every day. So everything has to happen in real time. There's no time to say that, okay, let's store the data and today's data will process tomorrow. That's simply, you have to shut down the telescope tomorrow if you need to do that. So the throughput is going to be limited by the rate at which data can be processed and delivered to the external regional centers. So here one is forced to think of the science data processor as an integral part of the telescope, because the data reduction can not ever interrupt or constrain the data acquisition. In planning the observing program, the science data processor therefore must become a schedulable resource of the telescope itself. So the data, once it is processed at the science data processing centers located in the host countries, will flow over a network of undersea optical fibers to a number of regional centers. Together they form what is called the SRC network. These will be located all around the globe, and we hope to have one such node in India. These SKA regional centers are required because the observatory data products that are emerging from the telescope will need to be visualized, they need to be analyzed, they need to be modeled, and so on. And the data volumes are so large that the traditional model of simply delivering the raw data to the user, which we do with telescopes like the GMRT, is simply not going to be feasible. The community of scientists that are working on the SKA science data are also globally distributed. They're all over the world. And therefore, it's important that we develop a network of SKA regional centers that can cater to all these constraints and requirements. What will these regional centers provide? They will provide a platform for doing collaborative science, and they will provide a transparent and location agnostic interface to users. So what that means is people will access the data from the SKA using a common science portal. So it will be a bit like we log into Gmail and all our email is sitting there. We don't really care whether the email physically is sitting in California or it's sitting in somewhere else. we are just getting a uniform user experience just by accessing the data. So similar things will be provided to the users of the SKA. The SRC network will also be a location for software analysis, modeling, visualization, algorithm development, etc., etc. And it'll also provide user support. So the SKA regional centers in the data flow vertical, they'll maintain the flow of data out of the observatory and to the community. In the data processing side, they will provide compute resources to the users to allow them to analyze their data and to create advanced data products. It will also be a data storage facility because it will store one copy of the data, and it will allow for discovery science, perhaps from non-SKA users. So citizen science projects, etc., could be supported that way. They will also provide support to users. The SKA Observatory has a quick timeline. In February 2021, the SKA was born. Construction proposal was approved in June 21. Construction activities began immediately. By November 22, 42 major work contracts were awarded, including some to India, with a value of more than 200 million euros. And more major contracts are being prepared. And on the 5th of December last year, there was a construction commencement ceremony, which marked the official start of construction. These are the sort of milestone events in the telescope. The table on the right tells you on what dates different milestones will be reached. AA 0.5 is the first milestone in 2024. AA2 in 2026 is going to be an important milestone, as we shall see in a minute. And then what's going to happen is every milestone will be maintained, it will be kept operational, and the facility will be continuously expanded. While all of this is happening, there is going to be science commissioning operations which will start. Then science verification will happen, and shared risk sort of cycle zero observations will also commence by about 2027. So in science commissioning, one is going to just make sure that the telescope is working. Science verification involves a number of steps that all the proposed observing modes are functional, and then they are providing the kind of data that we expect. These data will be publicly released so that the worldwide community can access the data. Then there will be the shared risk PI projects, and then eventually the principal investigator-driven projects and key science projects will kick in. By about mid-2026, when AA2 milestone is completed, both low and mid telescopes will become the most powerful telescopes of their kind. And so this is the SEFD is a figure of merit which measures how powerful a telescope is. And as you can see, the uGMRT at 700 megahertz will be overtaken by the SKA in 2026. Similarly, the LOFA telescope will be overtaken by SKA low also in 2026. Now I'll describe what we have been doing over the years. We have been directly contributing to the development efforts of the SKA since early 2010. We have had strong industry participation since the beginning. This is pretty unique for India because most of the other countries did not have very strong interaction with their respective industrial partners, whereas we have been interacting with them right from the beginning. Our biggest contribution so far, and perhaps in the future, is going to be in the area of the observatory management and control, which was led by NCRA. Way back in 2010-11, we led the concept design of the monitoring and control system. From 2013 to 18, we led the detailed design phase of the telescope manager, which I showed you a few minutes earlier, is the nerve center of the telescopes. From 2019, From 2019 to 22, which was the so-called bridging phase, we contributed one scaled agile team, which was working on low-level Tango-based monitoring and control software. And since April 2022, we have ramped up to 3 teams instead of 1. These are people from the industry, all working full-time. So we have about 25 people there. And one team is focused on the development of higher level software for observation management, for things like scheduling, user interfaces for proposal management, proposal submission, engineering user interfaces, operator user interfaces, and so on. While doing this, 2 teams are driving the development of the hardware level software and interfaces, and about 25% of SKA software will come from India. Here's a cartoon which tells you, again, emphasizes why the telescope monitoring and control is very important, because it's connected at the lower level with the telescope hardware itself, but it's also connected to the science data processor, and through that to the SKA Regional Centers, and so on. The green box, the telescope monitor and control, is where we are contributing 2 teams. We have a very, very significant role in developing this. We are in observatory science operations. We are contributing 1 team out of 3 teams. We also have other contributions to SKA engineering efforts. For the SKA low, some station level hardware integration and testing is being done. These are primarily receivers at the station level. This work is led by Prabhu from RRI and has significant participation from RRI and NCRA engineers. This is going to be work done that is done collaboratively with Italy. In addition, fabrication of SKA band 2 feeds will also likely happen in India, and this work is being discussed. This will be work in collaboration with Sweden. Indian scientists have gotten themselves organized, grouped together. They formed the SKA India Consortium. There are of the order of more than 20 universities and research institutions, which are now part of the SKIC. You can see we have a wide geographical distribution, except for the Northeast. Most of the country has been covered. Each member institution has 1 member as part of the SKIC Executive Committee, which is responsible for managing and coordinating all SKA-related activities in India. Indian scientists have organized themselves into science working groups. Many of these groups mirror the international working groups, in which also we have significant Indian participation. The current participation status is that we are operating under a cooperation agreement with the SKAO. This is pending the approval of our comprehensive 10-year proposal for Indian participation at about the 6% level in the SKA. This proposal is now at the final stages of approval with the central government. Our proposal covers all aspects of our participation. I did not speak about many of them because you would have heard about some of them from the other speakers. Our scientific engagement, our in-kind contributions of hardware and software to the engineering effort, the construction of a SKA Regional Center, the development of enormous human resources, so that when the telescope comes online, we have the right people in place to observe. Then public outreach. You probably heard a talk from Neeraj yesterday on that, and more. If you want to learn more, there is going to be a JOA special issue, which will soon be out. Some of the articles are already out on the website. This will have about 30 articles on Indian participation in the SKA. I'll just end by showing you some photographs which were taken recently across the world. There is a lot of work happening The first SKA dish foundations have been laid. In Australia, a prototype station has been constructed. The SKA dishes will soon be shipped to South Africa, where they will be put together. All kinds of testing facilities have been put together. I draw your attention to the subrack, which was delivered to GMRT and has undergone extensive integration and testing. Labs all over the world. The SKAO has acquired in both the countries, and now things are really rolling fast.
Long live India and France friendship.